Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the General Chemistry Review, Chapter 10, Acids and Bases. Definitions. Over the last century, chemists have used different definitions to identify compounds as acids or bases. 3 definitions emerged, with each more inclusive than the former one. Arrhenius. The first and most specific definition of an acid or base is the Arrhenius definition. An Arrhenius acid will dissociate to form excess protons in solution, and an Arrhenius base will dissociate to form an excess of hydrochloride. Is that what you call? Or not hydrochloride, oxy, what do you call OH again? Hydroxy ions. OH minus in solution. These behaviors are generally limited to aqueous acids and bases. Arrhenius acids and bases are easily identified. Acids contain H at the beginning of their formula, HCl, HNO3, H2SO4, and so on, and bases contain OH at the end of their formula, NaOH, CaOH2, FeOH3, and so on. Acid dissociates to form H+. Protons, hydroxide ions. So examples, HCl, HNO3, H2SO4. And examples of bases, NaOH, CaOH2, FeOH3. Bronsted-Lowry. A more inclusive definition of acids and bases was proposed independently by Johannes Bronsted and Thomas Lowry in 1923. Bronsted-Lowry. A Bronsted-Lowry acid is a species that donates hydrogen ions, while a Bronsted-Lowry base is a species that accepts them. Alright. The advantage of this definition over Arrhenius is that it is not limited to aqueous solutions. For example, OH, NH3, and F are all Bronsted-Lowry bases because each has the ability to accept a hydrogen ion. However, neither NH3 nor F- can be classified as Arrhenius bases because they do not dissociate to produce an excess of OH ions in aqueous solutions. According to both of these definitions, there is only one way for a species to be an acid producing hydrogen ions. The only differences between the two definitions for acids are the requirement of an aqueous medium in the Arrhenius definition and the acidity of water. In the Arrhenius definition, water is not considered an acid. It does not produce an excess of protons in solution. Water is, on the other hand, a Bronsted-Lowry acid because it is able to donate a proton to other species. Most acid-base chemistry reactions on the MCAT will involve the transfer of hydrogen ions in accordance with the Bronsted-Lowry definitions. So, acids are proton donors. Bases are proton acceptors. NH3 F minus bases. Or bases are BS bases, not Arrhenius. Bronsted-Lowry acids and bases always occur in pairs because the definition... You know what? I also want to put water. H2O is a BS... Take away that. Is a BS base acid, not an Arrhenius acid, though. Bronsted-Lowry acids and bases always occur in pairs because the definitions require the transfer of a proton from the acid to the base. These are conjugate acid-base pairs, as described in the next section. For example, in the autoionization of water, H3O plus is the conjugate acid and OH is the conjugate base, as shown in figure 10.1. All right. So, why don't I write down this equation? Autoionization of water into its conjugate acid and conjugate base. We have 2H2O becomes H3O plus and OH minus. And the H3O is the conjugate acid. Should we make bases in blue? Conjugate base. All right. Lewis. At approximately the same time as Bronsted and Lowry's publications, Gilbert Lewis also proposed a definition for acids and bases. A Lewis acid is defined as an electron pair acceptor, and a Lewis base is defined as an electron pair donor. As shown in figure 10.2, the electron pair being donated is a lone pair and is not involved in any other bonds. Lewis proposed that an acid is an electron acceptor and a base is an electron donor. So we have a Lewis acid, BF3, and a Lewis base, NH3, and the lone pair on the nitrogen is transferred to the boron, making a Lewis acid-base compound. On the MCAT, Lewis acid-base chemistry appears with many names. The underlying idea is that one species pushes a lone pair to form a bond with another. This same chemistry can be called coordinate covalent bond formation, discussed in Chapter 3, complex ion formation, discussed Chapter 9, or nucleophile-electrophile interactions, discussed in Chapter 4 of Organic Chemistry. So we'll get to that. So they're saying that coordinate covalent bonds are equivalent to complex ion formation, which is equivalent to nucleophile electrophile interaction. So in in organic chemistry, they call it nucleophile-electrophile interaction. Okay, we'll get to that. There is an intuitive approach to understanding the differences in the definitions we have discussed so far. The Lewis definition relies on a behavior that is not vastly different from the Bronsted-Lowry interactions. The only difference is the focus. For Bronsted-Lowry acids and bases, we follow the exchange of the hydrogen ion, which is essentially a naked proton. In the Lewis definition, the focus of the reaction is no longer on the proton, but instead the electrons forming the coordinate covalent bond. This difference can be seen using curved arrows as shown in figure 10.3. So in the Bronsted-Lowry case, you have the hydrogen going to meet the oxygen. In the other case, you have the electrons, a lone pair of electrons on the oxygen migrating to the hydrogen. In the Lewis case, they call it the attack of the electrophile. All right. Note that the Lewis definition is most inclusive. Every Arrhenius acid is also a Bronsted-Lowry acid, and every Bronsted-Lowry acid is also a Lewis acid. And likewise for bases. However, the converse is not necessarily true. The Lewis definition encompasses some species not included with the Bronsted-Lowry definition. For example, BF3 and AlCl3, aluminum chloride and trichloride and boron trifluoride, are species that can each accept an electron pair, which qualifies them as Lewis acids, but they lack a hydrogen ion to donate, disqualifying them as both Arrhenius and Bronsted-Lowry acids. On the MCAT, you may encounter Lewis acids in the context of organic chemistry reactions because Lewis acids are often used as catalysts. Let's draw a diagram, just a Venn diagram of Lewis, Bronsted-Lowry, and Arrhenius. I spelled Arrhenius wrong. Arrhenius. Outside we have the Bronsted. Bronsted-Lowry and Lewis out here. Amphoteric species. An amphoteric species is one that reacts like an acid in a basic environment and like a base in an acidic environment. In the Bronsted-Lowry sense, an atmospheric species can either gain or lose a proton, making it amphiprotic as well. Amphoteric, amphiprotic. Acts like acid and base, amphiprotic. Gain or lose electron or proton. On the MCAT, water is the most common example. When water reacts with a base, it behaves as an acid. Water reacting with a base donates a proton. When water reacts with an acid, it behaves as a base, so it accepts a proton. The partially dissociated conjugate base of a polyvalent acid is usually amphoteric. The partially dissociated conjugate base of a polyvalent acid is usually amphoteric. For example, HSO4 can either gain a proton to form H2SO4 or lose a proton to form SO4. The hydroxides of certain metals, such as aluminum, zinc, lead, and chromium, are also amphoteric. Furthermore, species that can act as both oxidizing and reducing agents are often considered to be amphoteric as well, because by accepting or donating electron pairs, they act as Lewis acids or bases respectively. So let's write down amphoteric species, some examples of amphoteric species. Put HSO4 in there, as well as aluminum, zinc, lead, chromium. Complex amphoteric molecules include amino acids that have zwitterion intermediate with both cationic and anionic character, as shown in figure 10.4. Such species are discussed in great detail in chapter 1 of biochemistry. And we have amino acids zwitterion are complex amphoteric species. The amino group can release a proton, and the carboxylate group can accept a proton. So the amino is the acid and the carboxylate is the base. Let's write down zwitterion. Let's write down amino carboxylate. Yeah. Acid-base nomenclature. The names of most acids are related to the names of their parent anions. The anion that combines with protons to form the acid. Acids formed with anions with names that end in "ide" have the prefix hydro and the ending "ic", like fluoride, hydrofluoric acid, chloride, hydrochloric acid, bromide, hydrobromic acid. Nomenclature. Should we write this down? Now I'll remember this. Acids formed from oxyanions are called oxyacids. If the anion ends in "ite," except for oxygen, then the acid will end with "us," acid. If the anion ends in "ate," more oxygen, then the acid will end with "ic acid." Prefixes in the names of the anions are retained. Some common examples include the following. Hypochlorite, chlorite. So hypochlorite is hypochlorous acid. Chlorite is chlorous acid. Chlorate is chloric acid. Perchlorate is perchloric acid. Nitrite is nitrous acid. Nitrate makes nitric acid. Carbonate makes carbonic acid. Sulfate makes sulfuric acid. Phosphate, phosphoric acid. Borate, boric acid. Chromate, chromic acid. Acetate, acetic acid. These are some useful compounds that we should kind of know anyways, huh? We should memorize these. Compare and contrast the three definitions for acids and bases. Arrhenius acids dissociate into proton to make an excess of protons, and Arrhenius bases dissociate to make a surplus of hydroxide ions. Bronsted-Lowry acids and bases, the acids are protonic donors, bases are proton acceptors. Lewis acid is an electron acceptor, and a Lewis base is an electron donor. Utilizing Arrhenius acid naming trends, predict the acid formula and name for the following anions. Acid formula and name. So Mn is, what's Mn? Magnesium? No, that's magnesium. This is what's Mn? Manganese. Manganese perchlorate. Perchlorate is chlorate. Manganate. Permanganate. MnO4 would be permanganate. And the formula for the acidic form, I guess, acid formula is just HMNO4. Perchlorate, 4 oxygens takes just 1 hydrogen, so I guess it'd be the same for this, just 1 hydrogen. Permanganate. Permanganic acid. Permanganic acid. Permanganic. That's how I'm going to go with. Titanate would be HTiO3. And that would be called, titanate would be titanic acid. Titanic acid. Cool. Iodine, HI, would be hydroiodic acid. Hydroiodic iodine, iodic acid, hydroiodic acid. And HiO4 would probably be something like periodic acid. Yeah, sounds good. Identify which reactants are amphoteric species in the following reactions. For those species, determine if the compound is also amphiprotic. Amphoteric and amphoprotic. HCO3. So in this case, the amphoteric reactant is the H2CO3, or the HCO3, I guess, because it could further lose a hydrogen. Is it amphiprotic? Yes. Here we have HCl and OH, and we have H2O. So H2O is the amphoteric reactant. Is it amphiprotic? I guess so. H2O can also gain a proton to be H3O. Here the amphoteric reactant is, I guess again, H2O. This is in the presence of HCl, this is in the presence of HBr. Since this would be more acidic, I imagine, this is more basic because of all the OH. So in this case, if it's really basic, yeah, hydrogen can gain, or H2O can gain another hydrogen. So that's amphiprotic. In this case, is it amphiprotic? This is acidic, so it's probably not going to gain a proton beyond this. So we'll say no to amphiprotic for the third one. This is in, I guess, an acidic environment. And so also I don't know if this is going to lose another hydrogen. So maybe I'll say no for amphiprotic for the first one. No, yes, no. That's what I'm going to go with. Let's see the answers to these. Answers. Arrhenius dissociates to form excess protons. Arrhenius base dissociates to form excess hydroxide ions. Bronsted-Lowry acid is a proton acceptor. Bronsted-Lowry base is a proton acceptor. A Lewis acid is an electron acceptor, and a Lewis base is an electron donor. Number 2, the acid formula for permanganate is permanganic acid. The acid formula is HMnO4, and it's permanganic acid. H2TiO3 is titanic acid. HI is hydroiodic acid, and HiO4 is periodic acid. Number 3, the amphoteric reactant is HCO3 and it is amphiprotic. In the second one, the amphoteric reactant is the AlOH3 and it is not amphoteric, not the H2O, but the AlOH3. I see. Because it will accept I guess not in the sense, not in the I guess not in the Bronsted-Lowry case, but in the Lewis case, it's accepting electrons. So I guess amphiprotic is no. So it's not a Bronsted-Lowry acid base, but it's a Lewis acid base. It's not amphiprotic. Third one, the amphoteric reactant is the ZNO, zinc oxide. How many electrons does Br have? 7. It's got 2 of those, so it's donating electrons over here, and I guess accepting electrons over here. So this is the S, this is the base, and it's also not amphiprotic because it's not transferring protons, it's transferring electrons. We're tracking electrons here. All right. So I guess I was going with the Bronsted-Lowry. I was trying to go Bronsted-Lowry on these guys, but they're taking the Lewis case, I guess. All right. Properties. All right, properties. Acids and bases are usually characterized according to their relative tendencies to either donate or accept hydrogen ions. Furthermore, aqueous acid and base solutions can be characterized according to their concentrations of hydrogen and hydroxide ions. Autoionization of water and hydrogen ion equilibria. Because many acid-base reactions take place in water, especially on the MCAT, it is very important to understand the behavior of acidic and basic compounds in water. Only then can one fully appreciate the meaning and significance of such terms as strong acid, weak base, or measurements of pH and pOH. The acid-base behavior of water. As described above, water is an amphoteric species. In the presence of a base, it reacts as an acid, and in the presence of an acid, it reacts as a base. As an amphoteric compound, water can react with itself in a process called autoionization. Seen previously in figure 10.1, autoionization of water is represented by the equation 2H2O can autoionize into an H3O plus and an OH minus. One water molecule donates a hydrogen ion to another water molecule to produce the hydronium ion, H3O plus, and the hydroxide ion, OH minus. Many general chemistry courses depict the hydrogen ion simply as H plus rather than H3O plus. This is acceptable for representing the chemistry, but it is important to remember that the proton is never isolated in the solution. It is always attached to water or some other species that has the ability to accept it. Autoionization of water is a reversible reaction. Therefore, the expression above is an equilibrium for pure water at 298 Kelvin. The water dissociation constant Kw has been experimentally determined to be 10 to the minus 14 at 25 degrees Celsius. Should we write that down? The autoionization of water is in equilibrium, or the water dissociation constant, water dissociation constant, Kw, equals, which represents the autoionization of water into H3O and OH, which equals 10 to the minus 14 at 298 Kelvin. Each mole of water that autoionizes produces 1 mole each of hydrogen or hydronium ions and hydroxide ions, as the concentrations of the hydrogen ions and hydroxide ions are always equal in pure water at equilibrium. Thus, the concentration of each of the ions in pure water at equilibrium is at 298 Kelvin is 10 to the minus 7 moles. 10 to the minus 7 times 10 to the minus 7. However, the concentrations of the two ions will not always be equal. In fact, they will only be equal when the solution is neutral. Nevertheless, the product of their respective concentrations will always equal 10 to the minus 14 when the temperature of the solution is 298 Kelvin. For example, if a species donates hydrogen ions to pure water, the hydrogen ion's concentration will increase, causing the system to shift toward the reactants in the autoionization process. The result is a decrease in the hydroxide ion concentration and a return to the equilibrium state. This is Le Chatelier's principle in action. The addition of product to a system at equilibrium causes the system to shift away from the products and toward the reactants. The shift away from the products necessarily decreases the hydroxide ion concentration such that the product of the concentrations of the dissolved ions equals Kw. The addition of a species that accepts hydrogen ions results in a decrease in the hydrogen ion concentration and causes the system to shift towards the products, thereby replacing the hydrogen ions. This shift necessarily increases the hydroxide ion concentration and returns the system to equilibrium. Because we introduced the scales used in measuring concentrations of hydrogen and ions and hydroxide ions in different acid-base solutions, it is worthwhile to emphasize an important thermodynamic principle regarding the water dissociation constant expression. Kw is an equilibrium constant. Unless the temperature of the water is changed, the value for Kw does not change. Thus, the product of the concentrations of the hydrogen ions and the hydroxide ions in an aqueous solution at 298 Kelvin must always equal 10 to the minus 14. However, at different temperatures, the value of Kw changes. At temperatures above 298 Kelvin, Kw will increase. This is a direct result of the endothermic nature of the autoionization process. It's endothermic, and therefore, at higher temperatures, higher temp means that you have a higher Kw. All right. pH and pOH scales. The concentration of hydrogen ions and hydroxide ions in aqueous solutions can vary significantly, making the range of measurements on a linear scale unmanageable. The concentration scales for acidic and basic solutions are condensed into something more manageable through expression in logarithmic terms. These logarithmic scales are the pH and pOH scales for the concentrations of hydrogen and hydroxide ions, respectively. Using a logarithmic scale is not only mathematically convenient, but also useful for calculations. For instance, the reactivity of an acid or acidic solution is not a function of hydrogen ion concentration, but instead of the logarithm of the hydrogen ion concentration. pH and pOH are prototypical examples of p-scales. A p-scale is defined as the negative logarithm of the number of items. The pH and pOH of a solution are given by pH equals minus log of hydrogen ion or proton concentration, which equals the log of 1 over the proton concentration. And similarly, pOH is the negative logarithm of the hydroxide ion concentration, or the log of 1 over the hydroxide ion concentration. Let's write that down. pH equals minus log of H plus equals the log of 1 over H plus. And pOH equals minus log of hydroxide ion concentration, which equals a log of 1 over hydroxide ion concentration. For pure water at equilibrium and 298 Kelvin, the concentration of hydrogen ions equals the concentration of hydroxide ions, 10 to the minus 7 molar. Therefore, pure water at 298 Kelvin has a pH of 7 and a pOH of 7, because the minus log of 10 to the minus 7 equals 7. If we take the negative logarithm of the entire water dissociation expression, constant expression, H3O, the concentration of H3O plus and OH minus equals 10 to the minus 14, we find that pH plus pOH equals 14. pH plus pOH equals 14. For all aqueous solutions at 298 Kelvin, as pH increases, pOH decreases by the same amount. The relationship can be seen in figure 10.5 below. As pH goes up, pOH goes down. As pH goes down, pOH goes up. All right. For an aqueous solution at 298 Kelvin, a pH less than 7 or pOH greater than 7 indicates a relative excess of hydrogen ions and the solution is acidic. A pH greater than 7 or pOH less than 7 indicates a relative excess of hydroxide ions and the solution is basic. A pH and pOH equal to 7 indicates equal concentrations of hydrogen and hydroxide ions, resulting in a neutral solution. Estimating scale values. An essential skill to hone for test day is the ability to quickly convert pH to pOH, pK and pKa and pKb values into non-logarithmic form and vice versa. When the original value is a power of 10. The operation is relatively straightforward. Changing the sign on the exponent gives the corresponding p-scale value directly. For example, if H plus equals 0.001 or 10 to the minus 3, then the pH equals 3 and pOH equals 11. Or if Kb equals 1.0 times 10 to the minus 12, then pKb equals 12. Just like the 10 to the 7 here, makes a 7. More difficulty arises when the value is not an exact power of 10. Rest assured that the MCAT is not a math test and is not interested in determining your ability to perform complex logarithmic calculations. An exact logarithmic calculation of a number that is not an integer power of 10 is unnecessary on the MCAT. The test makers are interested, however, in testing the ability to apply mathematical concepts appropriately in solving certain problems. One can obtain a relatively close approximation of a p-scale value using the following shortcut. If the non-logarithmic value is written in proper scientific notation, it will be in the form n times 10 to the minus m, where n is a number between 1 and 10. Taking the negative logarithm and simplifying the p-value will be minus log of n times 10 to the minus m equals the negative log of n minus the log of 10 to the negative m, which equals m minus log n. Because n is a number between 1 and 10, its logarithm will be a decimal between 0 and 1. Log 1 equals 0, log 10 equals 1. The closer n is to 1, the closer log n will be to 0. The closer n is to 10, the closer log n will be to 1. As a reasonable approximation, one can say that the p-value equals m minus 0.n, where 0.n represents sliding the decimal point of n one position to the left, dividing n by 10. I'm going to write some of these down, where negative log of n times 10 to the minus m equals negative log n minus log 10 to the minus m. So this is separating out n times 10 to the minus m. And then the log of 10 to the minus m is just m minus, so we put that in front because it's a positive now, minus log n. Minus log n. And they're saying that minus log n part is just moving the decimal place over. And if that next, so the n part is the, what do you call this? In scientific notation, this part of it all right. Point is, anyways, let's write this part down as well, that the p-value is around m minus 0.n. P-value. Let's do an example where if K of A of an acid is 1.8 times 10 to the minus 5. And what is its pKa? And pKa is just the negative log of the concentration. Or of the Ka, not of the concentration. Negative log of 1.8 times 10 to the minus 5. So M is 5 minus 0. Then we'll take the 1.8. So like 1 or 2. We could round up to 2. Minus 0.2, which equals 4.8. So we're going to guess it's 4.8. They guessed it's 4.82. Actually, it's 4.74. Close enough. Strong acids and bases. Strong acids and bases completely dissociate into their component ions in aqueous solutions. For example, when sodium hydroxide is added to water, the ionic compound dissociates according to the net ionic equation. NaOH becomes Na plus OH. Hence, in a 1 molar NaOH solution, complete dissociation yields 1 mole of sodium and 1 mole of hydroxide ions. The pH and pOH for this solution can be calculated as follows. pH equals 14 minus pOH, which equals 14 minus negative log of OH, which equals 14 plus the log of 1 molar solution, which equals 14 plus 0, which equals 14. Virtually no undissociated strong acid or base, such as NaOH, will remain in solution. This is why the dissociation of strong acids and bases is said to go to completion. In the NaOH example above, we assume that the concentration of OH from the autoionization of water is negligible due to addition of a strong base. The contribution of OH and H from the autoionization of water is negligible if the concentration of acid or bases is significantly greater than 10 to the minus 7 molar. On the other hand, if the concentration of acid or base is close to 10 to the 7 molar, then the contribution from the ionization of water, the autoionization of water, is important. Calculate the pH of a 1 times 10 to the minus 8 molar solution of HCl. 1 times 10 to the minus 8 molar. HCl will dissociate into protons and chloride ions. So 1 times 10 to the negative 8 molar minus log of that. So 8 minus 0.1, 7.9. First, one may calculate the pH as minus log H plus, minus log 10 to the minus 8, so M is 8. However, this answer is not feasible. A pH of 8 cannot describe an acidic solution at 798 Kelvin because the presence of the acid will increase the hydrogen ion concentration to above 10 to the minus 7 molar, resulting in an acidic pH below 7. Should be below 7. Recognize that the acidic concentration in this question is actually 10 times less than the equilibrium concentration of hydrogen ions in pure water generated by the autoionization of water. Consequently, the hydrogen ion concentration from the water itself is significant and cannot be ignored. This can be represented in the equilibrium expression in which X represents the concentration of H3O plus and OH minus resulting from the autoionization of water. Solving for X, so here we have Kw, the autoionization of water, H3O plus times OH equals X plus 10 to the minus 8th times X, which equals 10 to the minus 14. Solving for X, which would require a quadratic equation, math that is beyond the scope of the MCAT, gives X equals 9.5 times 10 to the minus 8. The total concentration of hydrogen ions is 9.5 times 10 to the minus 8 plus 1 times 10 to the minus 8, which equals 10.05 times 10 to the minus 7. Notice that this is extremely close to the concentration of hydrogen ions in pure water. The pH of this acidic solution can now be calculated as the negative log of 1.05 times 10 to the minus 7th, which is around 7, but a little bit less, 6.9. This pH is slightly lower than 7 as expected for a very dilute acidic solution. The point of all this is stay alert and keep thinking critically no matter how familiar the problem setups might seem to you. So this can't be the case that you add HCl and it becomes 8 or it becomes 7.9. It goes from 7 to 7.9. It can't go up from adding HCl. So we added so little HCl that the chemistry of the autoionization of water is important. And so we have to consider H3O plus and HOH minus. Which equals X plus 10 to the minus 8. We're adding what we added plus what's already there. So in the autoionization of water, if we add protons, it's going to shift it to the left and make water out of it. Is that right? Yeah, that sounds right. So we added this much protons. But this number is probably going to be, so it's going to compensate, and X is going to be probably larger. Is that right? So this equals 10 to the minus 14 x plus 10 to the minus 8 times x equals 10 to the minus 14. How do you solve that? They said it's not on the scope, not in the scope of the MCAT. But you do something like x squared plus 10x 10 to the minus 8x minus 10 to the minus 14 equals 0. And then you do like x I don't even remember how to do this. A squared, or square root of plus or minus the square root of b. I don't even remember the quadratic formula. What is the quadratic formula? X equals minus b plus or minus the square root of b squared minus 4ac over 2a. So in this case, b is 10 to the minus 8th squared. So 10 to the minus 16th. Isn't there an easier way to do this? Can't we figure out how this factors? Two numbers that multiplied together make 14, but added together make 8. Added together twice. Anyways, we'll get back to this. We just know that x equals 9.5 times 10 to the minus 8th. And so the whole expression is 9.5 times 10 to the minus 8th plus 1.0 times 10 to the minus 8th, which equals 1.05 times 10 to the minus 7th. And the pH. So what is this? The total concentration of hydrogen ions is H plus total, which equals 9.5 plus 1. 1.5 times 10 to the minus 7th. Okay, that's just putting that plus 10 point to the minus 8 in there. pH is minus log 1.05 times 10 to the minus 7th, which equals 6.98. Great. Strong acids commonly encountered on the MCAT include hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, perchloric acid. Strong bases commonly encountered include NaOH, sodium hydroxide, potassium hydroxide, and other soluble hydroxides of group 1A metals. Calculation of the pH and pOH of strong acids and bases assumes complete dissociation of the acid or base in solution. Strong acids. HCl, HBr, HI, H2SO4, HNO3, HClO4, perchloric acid. And bases include NaOH, KOH, potassium hydroxide, and others. What is the pH of a solution of HClO4, 10 molar? Let's HClO4 equals 10, and pH is going to be just minus log of that, right? Which is what? Because there's no exponent, but I guess it's just 10 to the 1, so 1 will be the exponent. 1 times 10 to the 1. So 1 minus 0.1, so 0.9. Let's see what they do. Perchloric acid is a strong acid. It was fully dissociate in solution, therefore the concentration of protons is 10 molar. pH is minus log of 10, which is minus 1. This question points out that the pH scale does not end at 0 and 14. There can be negative pH values and pH values greater than 14, but this implies a very high concentration of a strong acid or base. So the answer is in fact -1. What did I do? I wanted to estimate that it was 1 times 10 to the 1. And so it's 1 minus 0.1. Shouldn't it be 0.9? But it's negative. I forgot the negative. Because in this case, the negatives cancel out to a positive. But in this case, since this isn't negative, this is negative. One. I would have said minus 1.1. Well, there you have it. -1. Weak acids and bases. Before going any further in our discussion of acids and bases, as strong or weak, verify that you are making the distinction between the chemical behavior of an acid or base with respect to its tendency to dissociate. That is, strong bases completely dissociate into aqueous solutions. And the concentrations of acids and base solutions, although we may casually describe a solution's concentration as strong or weak, it is preferable to use the terms concentrated and dilute respectively because they are unambiguously associated with concentration rather than chemical behavior. Okay. Continuing our focus on the chemical behavior of acids and bases, we will now consider those acids and bases that only partially dissociate in aqueous solution. These are called weak acids and bases. A weak monoprotic acid, HA, will dissociate partially in water to achieve an equilibrium state. Let us write this down. Weak acid plus H2O becomes H3O plus A minus. Because the system exists in an equilibrium state, we can write the dissociation equation to determine the acid dissociation constant. Ka equals H3O plus and A minus over HA. The smaller the Ka, the weaker the acid, and consequently, the less it will dissociate. Note that water as a pure liquid is not incorporated into the equilibrium expression. A weak monovalent Arrhenius base, BOH, undergoes dissociation to yield boron ions and hydroxide ions in solution. BOH becomes B plus, oh, this isn't boron. This is just a base, B and OH. BOH becomes B plus ions plus OH minus ions. The base dissociation constant Kb can be calculated as Kb equals B plus OH minus over BOH. So let's write this other half as well. An aqueous base will dissociate into hydroxide ions and its conjugate acid. And the Kb of such a dissociation will be B plus OH minus over BOH. The smaller the Kb, the weaker the base, and consequently, the less it will dissociate. As with the acid dissociation expression, water is not included because it is a pure liquid. Generally speaking, we can characterize a species as a weak acid if its Ka is less than 1, and as a weak base if its Kb is less than 1. On the MCAT, molecular, ionic, non-ionic weak bases are almost exclusively amines. Weak means that its Ka slash Kb is less than 1.0. And weak bases amines are weak bases. Conjugate acid-base pairs. Conjugate acid-base pairs. Because the Bronsted-Lowry definition of an acid-base reaction is one in which a hydrogen ion is transferred from an acid to a base, the two always occur in pairs called conjugates. A conjugate acid is the acid formed when a base gains a proton, and a conjugate base is the base formed when an acid loses a proton. For example, HCO3 plus H2O becomes CO3 and H3O. The CO3 is the conjugate base of HCO3, a weak acid, and H3O is the conjugate acid of H2O, a weak base. To find the Ka, we consider the equilibrium concentrations of the dissolved species. Ka equals CO3 times H3O divided by HCO3. The reaction between bicarbonate and water is reversible. The reverse reaction would be CO3 plus H2O becomes HCO3 plus OH. We can write the Kb for CO3 as Kb equals HCO3 times OH over CO3. If one adds the previous two reversible reactions, the net reaction is simply the dissociation of water. H2O becoming H3O and OH. Because the net reaction is the autoionization of water, the equilibrium constant for the reaction is Kw equals H3O times OH, which equals 10 to the minus 14, which is the product of Ka and Kb. Remember, the product of the concentrations of hydrogen ion and the hydroxide ion must equal 10.14, 10 to the minus 14. For acidic or basic aqueous solutions. Because water is an amphoteric species, both a weak acid and a weak base, all acid-base reactivity in water ultimately reduces to the acid-base behavior of water, and all acidic or basic aqueous solutions are governed by the dissociation constant for water. Thus, if the dissociation constant for one species or its conjugate is known, then the dissociation constant for the other can be determined using the following equation. The acid times the acid times the base will always equal 10 to the negative 14. An acid and a conjugate base, or a base times a conjugate acid, will equal 10 to the minus 14. This is evident from these equations. Ka and Kb are inverse related. In other words, if Ka is large, then Kb is small, and vice versa. But this logic, a strong acid, Ka approaching infinity, will produce a very weak conjugate base. For example, HCl is a strong acid, and the chloride ion is a very weak base. And a strong base will produce a very weak conjugate acid. For example, NaOH is a strong base, and H2O is a very weak acid. The conjugate of a strong acid or base is sometimes termed inert because it is almost completely unreactive. On the other hand, weak acids and bases tend to have conjugates that are also weak. As seen above, CO3 is a weak base, its conjugate acid, HCO3, is a weak acid. As it turns out, for this specific example, the reaction of CO3 with water to produce HCO3 and OH occurs to a greater extent, is more thermodynamically favorable than the reaction of HCO3 and water to produce CO3 and H3O. This fact makes this equilibrium ideal for buffering solutions as part of the bicarbonate buffer system. One important theme for acid strength is the effect of induction. Electronegative elements positioned near an acidic proton increase acid strength by pulling electron density out of the bond holding the acidic proton. This weakens proton bonding and facilitates dissociation. Thus, acids that have electronegative elements near to acidic hydrogens are stronger than those that do not, as shown in figure 10.6. So we have inductive effects from electronegative elements increase acidity. And we have a hydrocarbon, and what is this? An alcohol. So this is a alcohol with a pKa of 4.8. We have an alcohol with a chloride ion far from the proton that we're trying to dissociate. And that pKa is 4.5, went down. And then we move the chloride even closer. It's pulling electrons away. And so the proton more easily dissociates, and its pKa is 2.8. Oh, it's harder for it to dissociate. pKa is higher over here. Lower over here. Increase acidity. Oh, so it's higher over here. Inductive effects from electronegative elements. Chloride ion increasing, or the chlorine substitution of one of the hydrogens. Applications of Ka and Kb. Should we write some of this down? No. I want to write down that let's write down electronegative elements near proton increase acid strength, meaning they pull electrons, unshielding the proton. All right, applications. The most common use of acid and base dissociation constants is to determine the concentration of one of the species in solution at equilibrium. On test day, you may be asked to calculate the concentration of the hydrogen ion, the concentration of the hydroxide ion, or the concentration of either the original acid or base. Calculate the concentration of H3O in a 2 molar aqueous solution of acetic acid, CH3COOH. Note, Ka equals 1.8 times 10 to the minus 5. So, what we have here is CH3COOH, adding OH. But we want the concentration of H3O. So, in the dissociation of water into H3O plus and OH minus, we're adding OHs. So it's going to push it to the left. So the H3O is 2 molar. So water is pure, so we ignore it in concentration. But these, I guess, are both aqueous. So there's nothing on the bottom, but there's going to be an H3O term and an OH term. To the Ka of the acid. So we have 2 reactions. This reaction is just dissociation of acetic acid Is that right? Maybe not. It's O, and this is a proton. So it's going to lose a proton. Never mind, it's not going to add OH, it's going to add a proton. So it's going to be adding H3O. So this equation has a Ka of 1.8 times 10 to the minus 5. So that equals concentration of products, CH3COO and H, over reactants, CH3COOH, and what numbers do we put in here? Oh, concentration of H3O in a 2 molar aqueous solution of acetic acid. So the acetic acid, this at the bottom is 2. So 1.8 times 10 to the minus 5 equals CH3O CH3COO H over 2. So 1.8 times 2 is 3.6 times 10 to the negative 5 equals these two, CH3COO times H. And there's equal portions of both, I guess. So square root it. Rather than square root it, let's just write x times x in. (3.6) exponent of negative 5. Let's take the square root of that is 0.006. Or 6 times 10 to the minus third. So if that's the concentration of protons that we're adding, back to this first, so now we want the concentration of this. I guess it would just be this, right? No, it's that plus what's already there. And so a perfectly neutral solution will have a concentration of H3O of 7, right? So 1 times 10 to the minus 7. So that plus 6 times 10 to the minus 3. So should I add those two together? 0.006 and 0.1234. 6, 7. So that equals 0.006 006 0001 or 6.0001 times 10 to the third. I think that's what it would be, right? They did get an answer around 6 times 10 to the third. First write the equilibrium reaction. So that's the CH3COOH plus H2O becomes H3O plus CH3COO. Next, write the expression for the acid dissociation constant. Ka equals H3O plus CH3COO over CH3COOH. So the hydronium times the acetate ion divided by the acetic acid, which equals 1.8 times 10 to the minus fifth. Then recognize that acetic acid is a weak acid, so the concentration of CH3COOH, the acetic acid, at equilibrium is equal to its initial concentration, 2.0, minus the amount dissociated, X. Likewise, H3O equals CH3COO, which equals X, because each molecule of CH3COOH dissociates into one hydrogen ion and one acetate ion. Note that the contribution of the hydronium from water is negligible. Thus, the equation can be written as follows. Ka equals X times X over 2.0 minus X, which equals 1.8 times 10 to the fifth, negative fifth. Remember that the value of X is generally very small, therefore we can approximate that 2 minus X equals 2. This is further supported because acetic acid is a weak acid and only slightly dissociates in water. This simplifies the calculations to Ka equals X times X over 2, which equals 1.8 times 10 to the minus fifth. And so X squared equals 3.6 times 10 to the minus fifth, which equals 36 times 10 to the minus sixth. So X equals 6 times 10 to the minus third. So they said, don't even worry about this part, it's just this part. X represents the concentration of H3O, therefore H3O equals 6 times 10 to the minus third. Note, when needing to take the square root, adjust the coefficient as needed to make the power of 10 an even number. This way, the square root only requires cutting the power of 10 in half. All right. In this example, note that X is significantly lower than the initial concentration of acetic acid, 2 molar, which validates the approximation. Otherwise, it would have been necessary to solve for X using the quadratic formula. Fortunately, the value of X on test day is almost always sufficiently small to make this approximation. A rule of thumb is that the approximation is valid as long as X is less than 5% of the initial concentration. This typically occurs when Ka is at least 100 times smaller than the concentration of the starting solution. For example, if Ka is 10 to the minus fourth and the concentration of the starting solution is 0.01 molar or 10 to the minus 2 molar, then the ratio between the values is 10 to 2 or 100. The error in this calculation should be no more than 1 in 100, 1%. On the other hand, if Ka is 10 to the minus 3 and the concentration is still 0.01, then the ratio between the values becomes 10, which would lead to a 10% error. This degree of error may not be useful when identifying an answer choice on the MCAT. Students often feel nervous making the assumption that X is negligible because they want to see precise answer choices. However, keep in mind that the MCAT quite deliberately tests students' ability to make reasonable assumptions under timed conditions to arrive at a feasible answer choice. Part of the skill of taking the MCAT is rounding appropriately to simplify math. All right, salt formation. Acids and bases may react with each other to form a salt and often, but not always, water in what is termed a neutralization reaction. Neutralization, HA in aqueous form plus BOH in aqueous form makes Ba a salt plus H2O. All right. The salt may precipitate out or remain ionized in solution depending on its solubility and the amount produced. In general, neutralization reactions go to completion. The reverse reaction, in which the salt ion reacts with water to give back the acid or base, is known as hydrolysis. So this is a unidirectional reaction. The opposite is hydrolysis, and I guess I would assume that it takes energy, delta H, delta, you just put a delta, right? The reverse reaction, hydrolysis, four combinations of strong and weak acids and bases are possible. A strong acid and a strong base, like HCl and NaOH. A strong acid and a weak base, like HCl and NH3. A weak acid and a strong base, like HClO and NaOH. And a weak acid and a weak base, like HClO and NH3. Bicarbonate and ammonia are a weak acid and a weak base. The products of a reaction between equal concentrations of a strong acid and a strong base are equimolar amounts of salt and water. The acid and base neutralize each other, so the resulting solution is neutral. And the ions formed in the reaction will not react with water because they are inert conjugates. The product of a reaction between a strong acid and a weak base is also a salt, but often no water will be formed because weak bases are often not hydroxides. In this case, the cation of the salt is a weak acid and will react with the water solvent, reforming some of the weak base through hydrolysis. For example, reaction 1, HCl and NH3 becomes NH4 and Cl. Reaction 2, NH4 and H2O becomes NH3 and H3O. NH4 is the conjugate acid of a weak base, NH3, and is stronger than the conjugate base of the strong acid, chlorine. Chlorine in HCl. NH4 will then transfer a proton to H2O to form the hydronium ion. The increase in the concentration of the hydronium ion causes the system to shift away from autoionization, thereby reducing the concentration of hydroxide ion. Consequently, the concentration of the hydronium ion will be greater than that of the hydroxide ion at equilibrium, and as a result, the pH of the solution will fall below 7. This should make sense. A strong acid and a weak base produce a slightly acidic solution. On the other hand, when a weak acid reacts with a strong base, the pH of the solution at equilibrium will be within the basic range because the salt hydrolyzes with concurrent formation of hydroxide ions. The increase in hydroxide ion concentration will cause the system to shift away from autoionization, thereby reducing the concentration of the hydronium ion. Consequently, the concentration of the hydroxide ion will be greater than that of the hydronium ion at equilibrium, and as a result, the pH of the solution will rise above 7. Consider the reaction of acetic acid, a weak acid, and sodium hydroxide, a strong base. The acetic acid reacts with the sodium hydroxide to make sodium ions and acetate ions. Then the acetate ions will react with water to make acetic acid and excess hydroxide. The pH of a solution containing a weak acid and a weak base depends on the relative strengths of the reactants. For example, the weak acid HClO has a Ka of 3.2 times 10 to the minus 8, and the weak base NH3 has a Kb 1.8 times 10 to the minus 5th. Thus, an aqueous solution of HClO and NH3 is basic because the Ka for HClO is less than the Kb for NH3. That is, HClO is weaker as an acid than NH3 is as a base. At equilibrium, therefore, the concentration of hydroxide ion will be greater than the concentration of hydronium ions in the aqueous solution. In biology and biochemistry, neutralization reactions are often condensation reactions because they form bonds with a small molecule as a byproduct, usually water. The peptide bonds in proteins, for example, are created from the reaction of a carboxyl group, the acid, and an amino group, the base. while forming a water molecule, as shown in figure 10.7. The salt in this reaction is the polypeptide itself. Breaking it apart requires hydrolysis. All right. We're going to write some of these down. I guess this doesn't have to be with the delta. It's just about concentrate in Le Chatelier. An amphoteric species. Well, first I want to write down that amino acids form salts. We can remember that too. Carboxyl in amino. Carboxyl is the acid. What are on carboxyl? Carboxyl is the acid, and amino is the base. Acidic carboxylate reacts with an amino group. Acid and base neutralization. This is what's going on here to form peptide, which is the salt, and water. All right. What is an amphoteric species? It's a species that can be both an acid and a base. If a compound has a Ka value much greater than water, what does it mean about its behavior in solution? And how does this compare with a solution that has only a slightly higher Ka than water? If it has a greater solution, if it has a much greater Ka than water, then it will dissociate in water. It'll dissolve. And if it's just slightly higher than water, if some of it dissociates, that'll cause a reverse reaction. So some of it will reassociate. The opposite reaction will happen as well. If a compound has a Kb much greater than water, what does this mean? Same situation. It'll associate completely if it has a much greater Kb than water. And if it's only slightly greater, some of it will dissociate, but some of it will, the reverse reaction will also happen, and so you won't have too much of a change in the pH of the water, for example. Complete the blank cells in the table by utilizing the mathematical relationships between pH, pOH, and ion concentration. Note, round the numbers given and use logarithmic approximations to determine p-values with a calculator to simulate test day math. All right. A pH of 4 means a H3 concentration is negative log of concentration. Should you do an e to the 4? Or 10 to the 4? 10 to the minus 4? The POH is just 14 minus 4, 10. And so the concentration of OH should be ten to the minus 10. And so is it an acid or a base? It's an acid, right? Next one, 8.89. I should forget about the 8 part. Let's just put a 10 to the minus 4, 10, 10 to the minus 10, acid. POH of 5, 10 to the minus 5. 10 minus, or 14 minus 5 is 11. 10 to the minus 11. Base. Finally, 1 times 10 to the minus 6. 10 to the minus 6, 6. 12 minus, or 14 minus 6 is 8. No. I messed up this math, I realize. 14 minus 5 is 9. Let's make that a 9. And then, yes, let's make this an 8. Also a base. What is the mathematical relationship between Ka, Kb, and Kw? Ka plus Kb equals Kw. Ka plus Kb equals Kw. I guess. Identify the conjugate acid-base pairings in the reactions below. Acid-base pairings. So H2O is a weak acid. This is the base, and here's the acid. H3O is the acid, H2O is the base. H2CO3 is the acid, and HCO3 is the base. So acid, H2CO3, base, H2O, conjugate acid, H3O, conjugate base, HCO3. And down here, same thing, H2PO4 is the acid, H2O is the base, conjugate acid is, oh wait, this is a base, this is an acid. This is an acid, this is more acidic. So this is the acid, this is the conjugate base, this is the base. Oh no, this is the base, this is the conjugate acid. So this is the acid, this is the base. This is the conjugate base. This is the conjugate acid. So, acid, H2O, base, H2PO4, conjugate acid, H3PO4, conjugate base, OH. Determine the concentration of hydrogen ions and pH of a solution of 0.2 molar acetic acid for a Ka of 1.8 times 10 to the minus 5. 0.2 Ka equals 1.8 times 10 to the minus 5th. That equals acetic acid, CH3COOH, dissociating, right? And then those H pluses joining with water. So 0.2 molar acetic acid is adding 2 molar of this. Isn't that how they did it when they showed us how to do this? They combined the two together. We kind of failed to do it that way, but I guess what you're supposed to do is H3O. So this is not this. This is CH3COO. So we have 1.8 times 10. So these two numbers are the same. These two are x. This is 0.2, so it's x squared over 0.2 equals 1.8 times 10 to the minus 5th. 1.8 times 0.2 is 0.36 times 10 to the negative 5th, or 3.6 times 10 to the negative 4th, equals x squared. Square root of that. Did I do that right? 1.8 E5 times 0.2 and the square root of that. 8 times 10 to the minus fourth. So concentration of hydrogen ions, and pH is just negative log of that, which is 4 minus 0.8, 3.2. Well, that's the last problem. So let's check the answers. Atmospheric species can act as an acid, or amphoteric species can act as an acid or a base. High Ka indicates a strong acid, which will dissociate completely in solution. Having a Ka slightly greater than water means that the acid is a weak acid with minimal dissociation. Same thing for the bases. Let's check this grid of numbers. 4, 10 to the 4th, 10, 10 to the 10, 3.05, 8.89 times 10 to the minus 4th, 10, 1.12 times 10 to the minus 11th. I think we did an even better job of rounding than they did. So their numbers are more exact than ours. I like ours better. For the MCAT, ours are better. But the conclusions that the first two are acids and the next two are bases, those are the same. Ka times Kb equals Kw. Yeah, I put an addition there, but it should be multiplication. Because, yeah, 10 to the 7th times plus 10 to the 7th is just 10 times 10 plus 10, 20 to the 7th. But what we're doing is 10 to the 7th times 10 to the 7th. That's 10 to the 14th. That's what we're going for. All right. And here we have H2CO3 being an acid, H2O being a base, and so conjugate acid is H3O and conjugate base is HCO3. The second one we said H2O was the acid, so H2PO4 is the base, and then OH is a conjugate base and H3PO4 is a conjugate acid. Let's look at number 7. They got 3. We got 3. So we're pretty good. I made this a 4. It goes to 6. But I put it in the calculator anyway, so. (3.6 E6 equals square root of that is 8e minus 4. 8e minus 4. So we still got the same. Oh, they rounded 3.6, square root of 3.6 e6 to 2 times 10 to the minus third when it's 8 times 10 to the minus fourth. Three 3.6 e6 square root of that is 8e minus 4. I made it 2 times 10 to the minus 3. It's actually 1.9 times 10 to the minus 3. And pH equals 3 minus 0.2, 2.8. Our estimate ain't bad for the purposes of the MCAT. Polyvalence and normality. The relative acidity or basicity of an aqueous solution is determined by the relative concentrations of acid and base equivalents. An acid equivalent is equal to 1 mole of protons, and a base equivalent is equal to 1 mole of hydroxide ions. Some acids and bases are polyvalent. That is, each mole of the acid or base liberates more than one acid or base equivalent. Under the Bronsted-Lowry definition, such acids or bases could also be termed polyprotic. For example, the divalent diprotic acid H2SO4 undergoes the following dissociation in water. H2SO4 plus H2O becomes H3O plus HSO4, and then that HSO4 plus H2O becomes H3O and an SO4. 1 mole of H2SO4 produces 2 acid equivalents, 2 moles of H3O. Notice that the first dissociation goes to completion, but the second dissociation reaches an equilibrium state. The acidity or basicity of a solution depends on the concentration of acidic or basic equivalents that can be liberated. The quantity of acidic or basic capacity is directly indicated by the solution's normality, described in Chapter 9. For example, each mole of H3PO4 yields 3 moles equivalents of H3O. Therefore, a 2 molar H3PO4 solution would be 6N. Another measurement useful for acid-base chemistry is gram equivalent weight from Chapter 4. The gram equivalent weight is the mass of a compound that produces one equivalent, 1 mole of charge. For example, H2SO4 with a molar mass of 98, a divalent acid. So each mole of the acid compound yields 2 acid equivalents. The gram equivalent weight is 49 grams. That is, the complete dissociation of 49 grams of H2SO4 will yield 1 acid equivalent, 1 mole of H3O. Common polyvalent acids include H2SO4, H3PO4, and H2CO3. Common polyvalent bases include AlOH3, CaOH2, and MgOH2. Polyvalent acid, which include H2SO4, P3, H3PO4, and H2CO3. Common polyvalent bases include AlOH3, CaOH2, and MgOH2. All right. What species are considered the equivalents for acids and bases, respectively? An acid equivalent is anything that makes 1 mole of protons, and anything that's a base is anything that makes 1 mole of hydroxide ions. Calculate the normality of the following solutions. 2 molar of AlOH3, since it makes 3 equivalents of OH, it is 6N, 2M, 1, 2, 3. Yeah, 1, 2, 3 to 1 of these is 6N, and 16M for H2SO4, you get 2, so it'll be 32N. 6N and 32N. Should we check those? .3 Acids use moles of hydrogen, bases use moles of hydroxide. 2 AlOH3 is 6N, and H2SO4 is 32N. Great. Titration and buffers. I need to go to the bathroom real quick, get some water, and then we'll continue. All right, titration and buffers. Oh, I lost my pen. All right, we're back now. Titration and buffers. Titration. Titration is a procedure used to determine the concentration of a known reactant in a solution. There are different types of titrations, including acid-base, oxidation reduction, and complexometric, metal ion. The MCAT frequently tests the first two types. Complexometric, the metal ion titrations, are outside the scope of the MCAT, but focus on formation of complex ions as described in Chapter 9. So we'll be dealing with acid-base and oxidation reduction. General principles. Titrations are performed by adding small volumes of a solution of known concentration, the titrant, to a known volume of a solution of unknown concentration, the titrand, until completion of the reaction is achieved at the equivalence point. So, titrant is the known species, and the titrand is the unknown. Acid-base equivalence points. In acid-base titrations, the equivalence point is reached when the number of acid equivalents present in the original solution equals the number of base equivalents added, or vice versa. It is important to emphasize that while a strong acid, strong base titration will have its equivalence point at a pH of 7, the equivalence point does not always occur at a pH of 7. When titrating polyprotic acids or bases, discussed later in this chapter, there are multiple equivalence points as each acidic or basic conjugate species is titrated separately. This is shown in the speciation plot in figure 10.8. At the equivalence point, the number of equivalents of acid and base are equal. This fact allows us to calculate the unknown concentration of the titrand through the equation NaVa equals NbVb. NaVa equals NbVb, where Na and Nb are the acid and base normalities, respectively, and Va and Vb are the volumes of acid and base solutions, respectively. Note that as long as both volumes use the same units, the units do not have to be liters. So what we have here is volumes and normality. The equivalence point in an acid-base titration is determined in two common ways: evaluating by using a graphical method, plotting the pH of the unknown solution as a function of added titrand by using a pH meter, or estimated by watching for a color change of an added indicator. Indicators. Indicators are weak organic acids or bases that have different colors in their protonated and deprotonated states. This small structural change, the binding or release of a proton, leads to a change in the absorption spectrum of the molecule, which we perceive as a color change. Indicators are generally vibrant and can be used in low concentrations without significantly altering the equivalence point. The indicator must always be a weaker acid or base than the acid or base being titrated. Otherwise, the indicator would be titrated first. The point at which the indicator changes to its final color is not the equivalence point, but rather the end point. If the indicator is chosen correctly and the titration is performed well, the volume difference between the endpoint and the equivalence point is negligible and may be corrected for or simply ignored. Acid-base titrations can be performed for different combinations of strong and weak acids and bases. Most useful combinations involve at least one strong species. Weak acid, weak base titrations can be done, but are not very accurate and therefore are rarely performed. The pH curve for the titration of a weak acid, weak base lacks the sharp change that normally indicates the equivalence point. Furthermore, indicators are less useful because the pH change is far more gradual. strong acid and strong base. Let's consider the titration of 10 milliliters of 0.1 normal solution of HCl with 0.1 N solution of NaOH. Plotting the pH of the solution versus the quantity of NaOH added gives the curve shown in figure 10.9. Because HCl is a strong acid and NaOH is a strong base, the equivalence point of the titration will be at 7, and the solution will be neutral. Note that the endpoint shown is close to, but not exactly equal to, the equivalence point. Selection of a better indicator, one that changes colors at, say, pH of 8, would have given a better approximation still. The amount of error induced by the use of an indicator that changes color around pH 11 rather than pH 8 is not especially significant. It represents a mere fraction of a millimeter of excess NaOH. In the early part of the curve, when little base has been added, the acidic species predominates, so the addition of small amounts of base will not appreciably change either the OH or the pH. Similarly, in the last part of the titration curve, when an excess of base has been added, the addition of small amounts of base will not change the OH significantly. I think they mean small amounts of acid will not change the OH significantly, and the pH will remain relatively constant. The addition of base will alter the concentrations of H and OH near the equivalence point. So no, they're just talking about base. And will elicit the most substantial changes in pH in that region. Remember, the equivalence point for strong acid, strong base titrations is always at pH 7 for monovalent species. If one uses a pH meter to chart the change in pH as a function of volume of titrand added, a good approximation can be made of the equivalence point by locating the midpoint of the region of the curve with the steepest slope. Weak acid and strong base. Titration of a weak acid such as CH3COOH, acetic acid, with a strong base such as sodium hydroxide produces the titration curve shown in 10.10. Compare 10.10 with the curve in 10 and 9. The first difference is that the initial pH of the weak acid solution is greater than the initial pH of the strong acid solution. Weak acids do not dissociate to the same degree that strong acids do. Therefore, the concentration of H3O will generally be lower and pH will be higher in an equimolar solution of weak acid. Second difference is the shapes of the curves. The pH curve for the strong acid, strong base titration shows a steeper, more sudden rise in pH at the equivalence point. In the weak acid, strong base titration, the pH changes gradually early on in the titration and has a less sudden rise at the equivalence point. The third difference is the position of the equivalence point. While the equivalence point for a strong acid, strong base titration is pH 7, the equivalence point for a weak acid, strong base titration is above 7. This is because the reaction between the weak acid and strong base produces a weak conjugate base and even weaker conjugate acid. This produces a greater concentration of hydroxide ions and hydrogen ions at equilibrium due to the common ion effect on the autoionization of water. Therefore, the equivalence point for weak acid, strong base titration is always in the basic range of the pH scale. All right. Now, strong acid with a weak base. Appearance of the titration curve for a weak base titrant and strong acid titrant will look like an inversion of the curve for a weak acid titrant and strong base titrant. The initial pH will be in the basic range, typically pH 10 to 12, and will demonstrate a gradual drop in pH with the addition of strong acid. The equivalence point will be in the acidic pH range because the reaction between the weak base and strong acid will produce a weak conjugate acid and even weaker conjugate base. As shown in figure 10.11, the stronger conjugate acid will result in an equilibrium state with a concentration of hydrogen ions greater than that of the hydroxide ions. Therefore, the equivalence point for a weak base strong acid titration is always in the acidic range of the pH scale. Weak acid and weak base. The appearance of a titration curve for a weak base titrand and weak acid titrant will look like an intermediate of the previous types discussed. Because both the titrant and the titrand are weak, the initial pH is generally in the 3 to 11 range and will demonstrate a very shallow drop at the equivalence point. The equivalence point will be near neutral pH because the reaction is partially dissociative for both species. Polyvalent acids and bases. The titration curve for polyvalent acids or bases looks different from that for a monovalent acid or base. Figure 1012 shows the titration of Na2CO3 with HCl, in which the divalent diprotic acid H2CO3 is the ultimate product. In region 1, little acid has been reacted. In region 1, little acid has been added and the predominant species is CO3. In region 2, more acid has been added and the predominant species are CO3 and HCO3 in relative equal concentrations. The flat part of the curve is the first buffer region, discussed in the next session, corresponding to the pKa of HCO3, which is 5.6 times 10 to the negative 11th, and a pKa of 10.25. The center of the buffer region, the point between regions 1 and 2, is sometimes termed the half equivalence point, because it occurs when half of a given species has been protonated or deprotonated. Region 3 begins with the equivalence point, at which all of the CO3 is finally titrated to HCO3. As the curve illustrates, a rapid change in pH occurs at the equivalence point between 2 and 3. In the latter part of region 3, the predominant species is HCO3, although some H2CO3 has formed as well. At the beginning of region 4, the acid has neutralized approximately half of the HCO3, and now H2CO3 and HCO3 are in roughly equal concentrations. This flat region is the second buffer region and second half equivalence point between regions 3 and 4. If the titration curve corresponding to the pKa of H2CO3, Ka is 4.3 times 10 to the minus 7th, and pKa is 6.37. Region 5 starts with the second equivalence point, as all of the HCO3 is finally converted to H2CO3. Again, a rapid change in pH is observed near the equivalence point, the point between 4 and 5, as acid is added. The titrations of the acidic and basic amino acids, which have acidic or basic side chains respectively, will show curves similar to the one shown in figure 1012, but rather than 2 equivalence points, there will be in fact 3, one corresponding to the titration of the carboxyl group and a second corresponding to the titration of the amino group, both of which are added to the general carbon, as well as a third corresponding to either the acidic or basic side chain. All right. Let's write down that amino acids have 3 equivalence points. One for carboxyl, second for amino, and a third for the side chain. Carboxyl, amino, side chain. All right. Buffers. A buffer solution consists of a mixture of a weak acid and its salt, which is composed of its conjugate base and a cation, or a mixture of a weak base and its salt, which is composed of its conjugate acid and an anion. 2 examples of buffers that are common in the laboratory and commonly tested on the MCAT are a solution of acetic acid and its salt, sodium acetate, and a solution of ammonia and its salt, ammonium chloride. The acetic acid sodium acetate solution is considered an acid buffer, and the ammonium chloride ammonia solution is a base buffer. Base buffer solutions have the useful property of resisting changes in pH when small amounts of acid or base are added. Consider a buffer solution of acetic acid and sodium acetate. Note the sodium ion has not been included because it is not involved in the acid-base reaction. So you have acetic acid and H2O make hydronium ions and acetate ions. When a small amount of strong base, such as NaOH, is added to the buffer, like the OH ions, from the NaOH react with the H3O ions present in the solution. Subsequently, more acetic acid dissociates. The system shifts to the right, restoring the hydronium ions. The weak acid component of the buffer thereby serves to neutralize the strong base that has been added. The resulting increase in the concentration of the acetate ion, the conjugate base, does not create nearly as large an increase in hydroxide ions as the unbuffered NaOH would. Thus, the addition of the strong base does not result in a significant increase in OH and does not appreciably change the pH. Likewise, when a small amount of HCl is added to the buffer, protons from the HCl react with the acetate ion to form acetic acid. Acetic acid is weaker than the added hydrochloric acid, which has been neutralized by the acetate ions. So the increased concentration of acetic acid does not significantly contribute to the hydrogen ion concentration in the solution. Because the buffer maintains protons at approximately constant values, the pH of the solution is relatively unchanged. All right. So let's write down that acid buffer, common acid buffer is acetic acid. Acetic acid, CH3COOH, and its salt, which is sodium acetate, CH3COONA, and a common base buffer, basic acidic buffer and basic buffer. A good basic buffer is NH3 and NH4Cl. Which is ammonia and ammonium chloride. All right. The bicarbonate buffer system. In the human body, one of the most important buffers is the bicarbonate. The H2CO3 and HCO3 conjugate pair in the plasma component of the blood, called the bicarbonate buffer system. Specifically, carbonic acid and its conjugate base, bicarbonate, form a weak acid buffer for maintaining the pH of the blood within a fairly narrow physiological range. CO2, one of the waste products of cellular respiration, also has low solubility in aqueous solutions. The majority of the CO2 transported from peripheral tissues to the lungs, where it will be exhaled out, is dissolved in the plasma in a disguised form through the bicarbonate buffer system. CO2 and water react in the following manner. CO2 plus H2O makes bicarbonate, which makes protons and carbonic acid, or carbonate. Carbonic acid is H2CO3. Bicarbonate is just HCO3. So let's write that down. CO2 plus, we should write down that it's gaseous and it doesn't dissolve well in blood plasma. So it will bind to make carbonic acid, and then that will dissociate. We should put down that this is aqueous as well. And this will dissociate into aqueous protons and bicarbonate, also aqueous. And let's write down carbonic acid for the H2CO3 and bicarbonate for the HCO3. Carbonic acid, and why don't we turn this to blue for base? All right. The bicarbonate buffer system is tied to the respiratory system. In conditions of metabolic acidosis, production of excess plasma, protons not caused by the respiratory system itself, the breathing rate will increase to compensate and blow off a greater amount of carbon dioxide gas. This causes the system to shift to the left, thereby reducing protons and buffering against dramatic and dangerous changes to the blood pH. It is interesting to note that the bicarbonate buffer system, with a pKa around 6.37, maintains a pH around 7.4, which is actually slightly outside the optimal buffering capacity of the system. Buffers have a narrow range of optimal activity, plus or minus 1 pKa. This actually makes sense. It is far more common for acidemia, too much acid in the blood, to occur than alkalemia, too much base in the blood. As acidemia becomes more severe, the buffer system actually becomes more effective and more resistant to further lowering of the pH. The Henderson-Hasselbach Equation. Should we write down that metabolic acidosis will lead to increased CO2, less CO2 in the blood. Blowing off CO2, increased breathing rate means less CO2. Which will cause an increase in pH. The Henderson-Hasselbach Equation. Henderson-Hasselbach. Hasselbalch. A Henderson-Hasselbach equation is used to estimate the pH or pOH of a buffer solution. For a weak acid buffer solution, pH equals pKa plus log base divided by conjugate acid. I guess it's conjugate base and acid. Weak acid buffer pH equals pKa plus log of A minus, which is the conjugate base, over HA, which is a weak acid. Where A is the concentration of the conjugate base and HA is the concentration of the weak acid. Note that when the conjugate base equals weak acid, the pH equals pKa because log 1 equals 0. This occurs at the half equivalence points in a titration, and buffering capacity is optimal at this pH. Likewise, for a weak base buffer solution, pOH equals pKb plus log of conjugate acid over weak base, where B is the concentration of conjugate acid, BOH is the concentration of the weak base. Similar to acid buffers, pOH equals pKb when conjugate acid equals weak base. Buffering capacity is optimal at this pOH. The Henderson-Hasselbach equation is, in reality, just a rearrangement of acid or base dissociation constants. So we have Ka equals H3A over HA, minus log Ka equals minus log Ka equals minus log of H3O, minus log of A over HA. pKa is pH minus log of A over HA, or pH equals pKa plus log of A over HA. So you just see how they derive the Hasselback equation. One subtlety of buffer systems and Henderson-Hasselbach calculations that usually goes unnoticed or is misunderstood by students is the effect of changing the concentration of the conjugate pair but not changing the ratio of their concentrations. Changing the concentrations but not their ratios. Clearly, changing the ratio of the conjugate base to the acid will lead to a change in the pH of the buffer solution. But what about changing concentrations while maintaining a constant ratio? What would happen if the concentrations of both the acid and the conjugate base were doubled? While the pH would not change, the buffering capacity, the ability to which the system can resist changes in pH, has doubled. In other words, addition of a small amount of acid or base to the system will now cause even less deviation in the pH. As mentioned earlier, the buffering capacity is generally maintained within 1 pH unit of the pKa value. Example. What is the pH of a solution made from 1 liter 0.05 molar acetic acid with a Ka of 1.8 times 10 to the minus 5th mixed with 500 milliliters of 1 molar acetate CH3COO minus. So we start out with see, we have a volume and molarity of acetic acid. We have a volume and molarity of acetate. All right, so I guess normality A, volume of A equals normality of B, volume of B. So they don't have A and B, they have initial and final. Initial is alright, the normality 0.05 and volume 1 of the initial equals, we don't know what the normality is, that's what we're looking for, but the final volume is 1 liter plus half a liter, so 1.5. 1 times 0.05 is 0.05 divided by 1.5. And F equals 0.03. So this is for CH3COOH. We do the same thing for the CH3COO for the base. We have a N1, I guess I don't gotta write that again. But we have an initial molarity, 1 molality rather, times 0.5 liters in this case equals, we're looking for NF times our final volume, once again 1.5. So 0.5 divided by 1.5, 0.3. 0.03 for the acid, 0.3 for the base. And then we use the Hasselback-Henderson equation. Where the pKa is what they gave us, (1.8 times 10 to the negative fifth). So minus log of 1.8 times 10 to the minus fifth plus log of concentration of base, 0.3, over concentration of acid, 0.03. Point 0.3 divided by 0.03 is 10. Log of 10 is 1. And we estimate a negative log of this to be 5 minus 0.1, 5. Plus 1, 5.9. One 8 would make it 4.82 plus 1 is 5.82. 5.82 is what they get as well. All right, there you have it. Describe each of the following parts of a titration curve. The buffering region, I guess that's the region where it's effective. Half equivalence point, that would be where half of the first product is created. At the equivalence point, you have equal amounts. The end point, it's half turned into the acid, in this case, into the product. For reaction involving a strong base and a weak acid, which of the following indicators would be best to indicate the endpoint of the titration? Circle the correct answer. A strong base and a weak acid. So it's going to be basic. So we want something in the basic range. 9.7 phenolphthalein would be the first one. In which part of the pH range, acidic, basic, or neutral, will the equivalence points fall for each of the following titrations? Strong acid and a weak base will be acidic. Strong base and a weak acid will be basic. Strong acid and a strong base will be neutral, and a weak acid and a weak base will be neutral. What is the purpose of a buffer solution? To soak up excess protons to resist the change in pH. What are the pH and pOH of a solution containing 5 milliliters of 5 molar benzoic acid at 6.3 times 10 to the minus fifth and 100 milliliters of 0.005 molar benzoate solution, which would be our base. So we'll do something similar. We'll do the NVNFVF. So for the first one, so we're going to go with milliliters, I guess. We could do that because we're allowed to do that. We have to pay attention to normality. We forgot that these are normality, and we just happen to get one. But benzoic acid, how many do we actually get? What is the stoichiometric ratio for benzoic acid? Yeah, so you get 1 proton per benzoic acid. So normality is equal to molarity in this case. We're just going to use milliliters. 5 times 5 equals 100 milliliters plus 5 milliliters is 105 milliliters is our final volume times NF, and F equals 25 divided by 105 equals 0.24 we'll go with, round up a little. And then for our base, we have 100 milliliters times 0.005 molar equals, once again, 105 final volume times NF, and F equals 100 times 0.005 is 0.5, that divided by 105, 0.0048. Round up again. Now our pH equals minus log of the pKa, 6.3 times 10 to the minus fifth, plus the log of our base divided by our acid, base 0.0048 divided by acid 0.24, .048 divided by 0.24 is 0.02. 2 times 10 to the minus 2. So the log of that is minus 2 minus 0.2. And this is going to be 5 minus 0.63. So our pH equals 5 minus 0.63 minus 2 minus 0.2. 2.7? 2.17 rather. Let's see how we did. (10)(4). The buffering region occurs when HA equals A and is the flattest portion of the titration curve. The half equivalence point is the center of the buffering region where HA equals A. The equivalence point is the steepest point of the titration curve and occurs when the equivalence of acid present equals the equivalence of base. The endpoint is the pH at which an indicator turns its final color. Phenolphthalein would be the preferred indicator for titration. Strong acid and weak base have an equivalence point in the acidic range. A strong base and a weak acid have an equivalence point in the basic range. A strong acid and a strong base have an equivalence point in the neutral range, and a weak acid and a weak base also have an equivalence point in the neutral range. In the acidic, neutral, or basic range, depending on the relative strengths of the acid and base. So I guess that one depends. A buffer solution is designed to resist changes in pH and has optimal buffering capacity within 1 pH point from its pKa. And then our last one, they got 11.4. Oh, the pH is 2.57. Actually 2.5. So close enough. All right. And finally, discrete questions. Number 1. Which of the following is not a Bronsted-Lowry base? If you recall Bronsted-Lowry, all right, let's adjust this a little. All right. Which of the following is not a Bronsted-Lowry base? So I'm looking for something that's a electron acceptor or electron donor, but not a proton acceptor, or not a proton acceptor makes it Bronsted, Lewis makes it, or an electron donor makes it a Lewis. So this would accept protons, this can accept protons, this can accept protons. I imagine this can also accept protons, but I guess I'll go with this one. HNO2, HONO. It's got to be D, because we know that the rest of them are, right? I think I even wrote these down. NH3, F, And oh, the H2O is an acid, not a base. It's a Bronsted-Lowry. Why did I put an S there? It should be an L. So we'll go with C, because it's the acid, it's not a base. Two. Which of the following is closest to the pH of a solution containing 5 millimolar H2SO4? H2SO4 is a weak acid. So it should have a high pH, not that low. Not 1, 2, or 3. I'm going to go with 4, D. 3. Which of the following represents chloric acid? ClO3? Oh, that's not the acid. So it's got to be the HClO3. Or is it HClO2? Let's go with HClO3. I could just flip back real quick, couldn't I? ClO3, HClO3, chloric acid. A. Which of the following bases is the weakest? KOH, NH3, CH3, NH2, or CaOH2? NH3, I want to say. So pulling away electrons makes it more acidic. So being neutral would make it more basic, not having those electronegative components. I'd say CH3NH2 is the weakest. Because I imagine the NH2 can become NH3 and then NH4. So it's one step behind NH3? I don't know. We'll find out. The function of a buffer is to maintain a neutral pH, resist changes in pH when small amounts of acid or base are added, slow down reactions between acids and bases, or speed up reactions between acids and bases. It's going to be B. Resist change. What is the pH of a solution with an ammonium concentration of 70 millimolar and an ammonia concentration of 712 millimolar? Note that pKb of ammonia is 3.45. So we got ammonium and ammonia, NH4 and NH3. Whose base is conjugate acid. So we said ammonium is 70 millimolar, NH3, the ammonia, is 712 millimolar, and the pKb is 3.45. So pH equals pKb POH. So first we'll get POH and then we'll turn it into pH. POH is pKb plus log of B over BOH. Conjugate acid, acid over base. pH equals, so remember this is POH. pKb plus log B plus over BOH. That looks good. So we have a pKb of 3.45 plus log of the base, or the acid, 712 over conjugate base, 70. Or conjugate acid over base. 712 divided by 70. I guess we'd make that 10. A log of 10 is 1. So 3.45 plus 1 equals 4.45. And they have a 4.45, it's B. We're going to go with B for number 6. 7, what is the approximate value of pKa1? It's between, pKa1 is going to be around 3. But less than 3, 2.9 is better than 3.8. 3.8 would be like up here. 2.9 would be down here. I'm going to go with 2.9. B. 8. At what pH is the second equivalence point? Second equivalence point at what pH? Around between 5 and 6. 5.9, that's good. 8 is going to be C. 9 is going to what is the approximate value of pKa2? Same answer. 5.5. What's the equivalence point again? The flat part is a buffer region. Center of the buffer region is the half equivalence point. So the flat part, the buffer region, is the pKa. All right, so pKa is going to be in the first buffer region. So it's going to be around, like, it's going to be less than 2. It's going to be like 1.9. So I'm going to change my answer of 7 to A. And then the second, at what pH is the second equivalence point is still between 5 and 6. 5.9 sounds good. So I'll still go with C. But the 9, what is the value of pKa2? That'll be here between 4 and 5. So yeah, 4.1 sounds good. We'll go with B on that one. 10, what is the gram equivalent weight of phosphoric acid? Phosphoric acid. H3PO4. So P is 31 plus 4 times 16 plus 3 hydrogens, 34, 64, 98. So is it 98? Or is it 98 divided by 3? Which is 32.7. 10B. 11. What is the hydronium ion concentration of a 2 molar aqueous solution of a weak acid, HXO2, with a Ka of 3.2 times 10 to the minus 5th? So pH equals pKa plus log. Should we use this one? So, weak acid HXO2, which is going to become XO2, is going to be your base, weak acid conjugate base. So it'll be base, conjugate base over acid. So negative log of H equals negative log of Ka plus log of base over acid. Should we just assume it's the same number since it's to Ka? So instead of doing this, let's go up here to this from no, because I have to start from the pKa, not the Ka. Ka equals weak acid base H3O. H3O A over HA. This equals Ka. That's what Ka is. So take this, put this up here. All right. So in this case, Ka is 3.2 times 10 to the minus fifth equals, we're looking for the H3O concentration, but we know the weak acid concentration, HA, is 2 molar, and so the acid concentration is 2 minus whatever has dissociated, and this is just what is dissociated. I bet they're going to tell you, you can probably just ignore X. It's probably small. So let's just do that. Let's ignore X. Just make it H3O plus the concentration over 2. So this times 2 is going to be 6.4 times 10 to the minus 5. Is that an option? 6.4 times 10 to the minus 5. That sounds right, yeah. 11A. 12. A solution is prepared with an unknown concentration of a theoretical compound with Ka of exactly 1. What is the pH of the solution? Well, if Ka is 1, then pKa, oh wait, no. pH equals pKa plus conjugate base over acid. Is this what we're supposed to be thinking about? So if the Ka, so the log of 1 is 0, the log of 1, P is negative log, so 1, 0, I guess is negative 0 is still 0, plus some amount. Yeah, I guess we can't know without knowing this portion, because it's 0 plus something. It could be 0 plus 7. It could be 0 plus 8. It could be 0 plus 6. I think there's not enough information in this case. So I'm going to go with D. All right. 13. Which of the following is not a characteristic of an amphoteric species? Amphoteric species can act as an acid or a base depending on its environment. Amphoteric species can act as an oxidizing or reducing agent depending on its environment. Is oxidizing or reducing the same? Sure. Amphoteric species are sometimes amphiprotic. Sure. Amphoteric species are always nonpolar. Maybe D is the one that's not characteristic. 14. What is the approximate pH of a 1.2 times 10 to the minus 5 molar aqueous solution of NaOH? So, how did I think about it? Did I ever turn this from POH to pH? I might not have. Number 6. Because we have to do something similar, turning POH into pH. This I ended up with 4.45, but that's POH. So 14 minus 4.5 is 9.5. So the answer is actually C, 9.5, not B. I almost got it wrong. This is POH, pH equals 14 minus 4.5, pH is actually 9.5. So let's change this answer to C. And let's not forget to do that to the end of this one. I guess I'd use the same equation. POH equals, oh, I don't have a pK this time. So I'm just using concentrations. pH is concentrations of pH is log of 1 over H. POH is negative log of concentration of OH. In this case, since it dissociates so well, we know that this is the concentration of OH, 1.2 times 10 to the minus 5. POH equals negative log. Negative log of this, which we know is 5 minus 0.12, 82. So pH equals 14 minus 4.82, which equals 9.28, or 9.8, sure. Whoops. Oh yeah, that's good. 9.08. C. 15. How many liters of 2 molar BaOH2 are needed to titrate a 4-liter solution of 6 molar H3PO4? So, 6 molar H3O4 they don't specify whether it's to its first or second equivalence point. So we'll just assume it's to one equivalence point. So 6 molar, 1 hydrogen. So the acid, so in our NaVa equals NbVb. Na is going to be 6. Volume is 4 equals, since we're going to get 2 OHs for every one of these, its normality is going to be 2 times 2, 4. And we're looking for the volume, which must be 6. And that's not an option. So let's go to the second equivalence point. Let's say we get 2 hydrogens off of each of these. 6 times 2, 12. If we make that a 12, then this is now a 12. And that is an option. So let's go with that, B. 24 is not an option, so we're not going to the third equivalence point. So let's check these. Number 1 is C, not D. Or D, not C, rather. Bronsted-Lowry base is defined as a proton acceptor. Ammonia, fluoride, and water are each Bronsted-Lowry bases. This HNO2 is a far better acid donating a proton solution. So while H2O can be a base or an acid, HNO2 is a far better acid than it is a base. So the answer is D, HNO2. 2 is B instead of D. First, convert the concentrations. Next, because sulfuric acid is a strong acid, we can assume that for the majority of sulfuric acid molecules, both protons will dissociate. Concentration of hydrogen ions is there for 2 times 5 times 10 to the minus third, or 10 to the minus second. The equation for pH is pH equals minus log H. If H equals 10 to the minus 2, then pH equals 2. Okay, so you can't just use millimolars. It has to be 5 times 10 to the minus 3. And you're supposed to use an equation. You're supposed to go pH equals negative log of H. And then this millimolar, 5 millimolar equals 5 times 10 to the minus 3 molar times 2, 10, or 1, 10 to the negative 2 molar. Because you get 2 protons off of every H2SO4. So then you do 2 minus 0.0, so just 2. So which equals negative log of 10 to the minus 2, which equals 2. So the answer is B, 2. All right. 3 is A, 4 is B, not C. Soluble hydroxides of group 1A and 2A metals are strong bases, eliminating choices A and D. Choice B and C are both weak bases. However, methylamine contains an alkyl group, which is electron donating. This increases the electron density on the nitrogen in methylamine, making it a stronger Lewis base. Therefore, ammonia is the weakest base. I thought this thing would be a weak base, but ammonia is the weaker base. 5 is B. 6 is D, not C. Let's see what we did here. We got the POH is the pKb plus the log of the conjugate acid over the base, which is 3.45 times the log of 70 over 712. I reversed the acid and the base. This is base. This is acid. So this term should be 70 over 712. So 3.45 would not be raised to 4.5, but would instead be lowered to 2.45. And then the pH would be 14 minus 2.5, making it 11.5. Which is D, 11.5. So, mind your acids and bases. 7 is A, 8 is C. 9 is B, 10 is B, 11 is D, not A. So this question requires the application of the acid dissociation constant. Weak acids do not completely dissociate completely. Therefore, all three species that appear in the balanced equation will be present in solution. Hydrogen ions and conjugate base ions dissociate in equal amounts. So H plus equals XO2. If the initial concentration of HXO2 was 2 molar and small amount X dissociates, we will have X amount of H3O and XO2 at equilibrium, and 2 molar minus X amount of HXO2 at equilibrium. So there Ka equals H3O X squared Alright, so I put the X in the wrong spot here. What they have is that the concentration of H3O is an X. So it's X times X, and the X down here is negligible. So this is 2 minus X. This is X. This is also X. So this X is not negligible. The 2 minus X, that X is negligible. But the X on top is not negligible because it ends up being squared. So this is also an X up here. This is also an X up here. So this is X squared. Now, this number, we're going to get the square root of it. So the answer is the square root of what I tried to get. 11. I thought it was 6.4. .4 E5. The square root of that is 0.004. 1, 2, 3, 4.6 times 10 to the negative 3, which is whoops, 11. So 3.2 times 2 is 6.4. Square root of that So they did a neat trick here where 64, where there's 6.4 times 10 to the negative fifth, they turned into 64 times 10 to the negative sixth, and then you could just half the exponent. .4 E5 negative equals 0.00064. And the square root of that is 0.008. 1, 2, 3. So yes, the answer does end up being 0.008. So I got a x squared here. So the concentration of 830 equals the square root of this, which equals 8 times 10 to the negative third. All right, 12 is C, not D. Let's take a look at it. A higher Ka implies a stronger acid. Weak acids usually have a Ka that is several orders of magnitude below 1. pKa of a compound is the pH at which there are equal concentrations of acid and base. The pKa of this compound would be minus log 1 equals 0. With such a low pKa, this compound must be an acid. Therefore, the pH of any concentration of this compound must be below 7. So weak acids usually have a Ka that is a lot less than 1. Having a Ka of 1 implies that it's a strong acid. The pKa is a pH at which there are equal concentrations of acid and conjugate base. So, if its Ka is 1, its pKa is 0. And 0 is the pH at which there are equal concentrations of acid and base. So its equivalence point is at 0. With such a low pKa, this compound must be an acid. Therefore, the pH of any concentration of this compound must be below 7. So the answer is C. 13 is D, 14 is C, and 15 is C, not B. Here it says use the equivalence point. NaVa equals NbVb. BaOH2 can dissociate to give 2 hydroxide ions, so it is normally 2 times 2, 4N. So the 4 is right. H3PO4 can dissociate to give 3 hydronium ions, so its normality is 6 times 3, 18. So I made that a 12. Meaning the second equivalence point, but it's supposed to be the third equivalence point, 18. So this should also be 18. C. All right. Well, there you have it. That's acids and bases. Next time, Oxidation reduction reactions.